Hello everyone, this lesson is about current and drift velocity. You will have done some work on current already, and this is building that understanding, and we're going to find out what is meant by drift velocity, be able to calculate charge carrier density in a metal given the size of one atom, know and use the equation I equals nAqv, so we'll define each term and see how that equation works and where it comes from. Apply the equation I equals nAqv to explain the effect of temperature on the resistivity of metals and thermistors. So even at normal temperatures, with no current flowing, electrons move around continuously, colliding with ions within the lattice structure. The collisions with ions causes them to change direction and makes the motion completely random. Because they're all moving in all different directions completely randomly, there's no net transfer of energy, and there's no overall drift of electrons in any one direction. So there's no movement of charge through the material at all that can be detected. When a current flows, the electrons move generally in the same direction, not completely all going in the same direction, but overall there is a drift in one direction, the direction in which the current is flowing. And we can define something called drift velocity. Drift velocity is the average velocity of all the electrons in the circuit. So we're now going to define something called carrier density, which is all to do with how many charge carriers there are in a meter cubed of a material. If we consider a copper atom, we know atoms are really small. The diameter of a copper atom is about 0.25 nanometers. A nanometer is 10 to the minus 9 meters. So 0.25 times 10 to the minus 9 meters, or 2.5 times 10 to the minus 10 meters. I'd like you to pause the video and have a think about these questions. How can we calculate the number of copper atoms that would fit along a 1 meter single line of atoms with no spacings in between? How could we calculate the number of copper atoms in a 1 meter squared area? So just on the surface of a 1 meter square area, one atom thick, how many would we fit? Again with no spacings. And how can we calculate the number of copper atoms in a meter cubed? So if the diameter of a copper atom is about 0.25 nanometers, this means that there will be 1 divided by 0.25 nanometers, which equals 4 times 10 to the 9 copper atoms in 1 meter. Considering a cube of the copper of size 1 meter, theoretically, in this cube there must be 4 times 10 to the power of 9 cubed, which equals 6.4 times 10 to the power of 28 copper atoms. Assuming each atom has one free electron, there are 6.4 times 10 to the power of 28 free charges per cubic meter. This is called the charge carrier density and given the symbol N. Example, copper has a carrier density N equal to 6.4 times 10 to the 28. Each electron has a charge of 1.6 times 10 to the minus 19 coulombs. How much free charge would there be in a cubic meter of copper? So we simply multiply the charge carrier density by the charge of each electron. So 6.4 times 10 to the 28 charge carriers per meter cubed multiplied by the charge on each electron, which is 1.6 times 10 to the minus 19, gives 1.024 times 10 to the power of 10 coulombs. There are 2 practice questions now for you to have a go at. So pause the video and have a go at these, and then before you move on, the answers will be appearing when you press play. Answers to questions. Question 1. If n equals 4 times 10 to the 29 and the charge of each electron is 1.6 times 10 to the minus 19 coulombs, how much charge, free charge is in a cubic meter. So we multiply the two together, and we get 6.4 times 10 to the 10 coulombs. Question 2. So given the diameter of the atoms, it's a different metal. Assume each atom has one free electron again. So for this one, we know the diameter of the atom, so we can work out how many there will be in a meter cubed, like we did in the first example. So in 1 meter, there would be 1 divided by 0.5 times 10 to the minus 9 atoms, which equals 2 times 10 to the 9. In a meter cubed, we would need to cube that value. So there would be 2.0 times 10 to the 9 cubed, which equals 8.0 times 10 to the 27. Each atom has 1 electron, so there are 8.0 times 10 to the 27 charge carriers. So n equals 8.0 times 10 to the 27. So we've already defined drift velocity as the average velocity with which electrons will move down a wire. But how do we work it out? We can't actually measure the speed of individual electrons. Have a think about how this could be done. Consider a wire of cross-sectional area A and charge carrier density n, where each carrier has the charge q and they are moving with a drift speed of v. Number 1, every second the volume of charge carriers that passes a point will be equal to AV. That's cross-sectional area multiplied by drift velocity. Think about the units of that. Area is in meters squared. Velocity is meters per second. That's going to give us meters cubed per second, which is the volume per second. Therefore, the number of charge carriers that pass by every second is given by nAV. So it's the volume that passes by every second multiplied by the number per unit volume. And that will give us the number of charge carriers that pass by every second. 3. Therefore, the charge that passes by every second will be equal to nAVQ. So we've got the number of charge carriers from part 2. Part 3, just multiply that by the charge Q on each electron, and that gives us the charge that passes by every second. But charge per second is current. So that means we can write this as an equation. I equals nAqv. I is current, n is carrier density, A is cross-sectional area, Q is the charge on each charge carrier, and V is the drift velocity. Example, calculate the current down a 1 mm squared wire, that's the area, where the drift speed is 1 mm per second, and the carrier density n is 6.4 times 10 to the 28 per meter cubed. The charge on an electron is 1.6 times 10 to the minus 19 coulombs. Pause the video and see if you can do this. So let's just note down what we're given. So area, cross-sectional area is 1 mm squared. Drift velocity is 1 mm per second. N is 6.4 times 10 to the 28 per meter cubed. Q is 1.6 times 10 to the minus 19. We're asked to find I. So we can use the equation I equals nAqv. We multiply all the values together, but one thing to remember is that we need to convert area and drift velocity to meters, because n, which is our carrier density, has units of per meter cubed. So we've got to be putting the same units into the equation. So that would be 6.4 times 10 to the 28, which is n, times 1 times 10 to the minus 6, which is the area in meters squared, times 1.6 times 10 to the minus 19, which is q, charge on the electron, times 1 times 10 to the minus 3 meters per second, which is the velocity. That gives us 10.24 amps. So well done if you got that right. Here are two practice questions using this equation for you to have a go at. Pause the video, give them a try. Remember to show all of your working. So here is the working for the first question. So we're using the equation I equals nAqv, and we need to find n. So we can substitute and solve, or we can rearrange and then substitute. So n equals I divided by aqv, and we'll put the values in, but remembering to convert area from millimeters squared to meters squared, and velocity from millimeters per second to meters per second. So care is needed with that. And that will give you a value of n equal to 4.46 times 10 to the 27 per meter cubed. Question 2 this time asks to calculate the area, the cross-sectional area of the wire, given the drift speed and current and carry density. So it's the same equation, but we're rearranging it to find A. So A equals I over nQV, working as shown here, again converting the drift speed to from millimeters per second to meters per second, and all of the other values we can put straight in, and we should get 3.9 times 10 to the minus 8 meters squared as our cross-sectional area. Comparing drift speeds, consider two wires of the same metal connected in series with a current flowing through. If the area of wire 2 is twice that of wire 1, which wire do you think electrons travel fastest in? So we know that in a series circuit, the current is the same through all parts of the circuit. So I1 equals I2, the current through material 1 equals the current through material 2. We can write the equation I1 equals M1A1 Q1V1 and I2 equals N2A2 Q2V2. So because I1 equals I2, we can make those two equations equal to each other, and we can do some cancelling because Q is a common value and so is N if it is the same material. And we cancel that down to A1V1 equals A2 times V2. So the cross-sectional area multiplied by the drift velocity is a constant. So what that means is, if we increase the cross-sectional area, we will decrease the velocity, just considering one circuit with a common current. Metal wires and temperature. Predict what will happen to the current as a metal gets hot. Try and use the equation in your prediction. So in a metal, the temperature doesn't affect the carrier density. The cross-sectional area is going to remain the same, and the charge is a fundamental value which won't change. So the only thing that can change is the drift velocity. As the metal gets hot, the drift velocity V will reduce due to ion vibrations increasing, and this reduces the current. So in the equation, if V is reducing and everything else is the same on the right hand side, then I will reduce. We know the effect of increasing temperature in a metal on resistance. We know that the resistance increases, and that's because of this. It's because the current reduces for any given potential difference. So we've met the two semiconductor resistors, the LDR and thermistor. For the thermistor, I'd like you to predict what would happen to N when the thermistor heats up. So this time with the thermistor, because it's not a metal, it's a semiconductor material, we will see temperature having an effect on the carrier density N. But I'd like you to predict what that effect would be. So in a thermistor, N will increase with temperature as more electrons become free to move through the material. This has the effect of increasing the current and reducing the resistance. And you can see the graph here shows resistance falling as temperature increases. So to summarize how current behaves in a thermistor and in a metal, I'd like you to just have a quick go at this gap fill and see if you can fill in the missing words. Quick check then, you can correct your own work if you need to. Increasing the temperature of a metal will increase the vibrations of the ions. This will increase the resistivity of the metal and decrease the current because it lowers the drift speed. You can see the arrow there pointing to the drift velocity in the equation. In semiconductors, the carrier density is small but increases with temperature. So the resistivity of a semiconductor decreases with temperature, e.g. a thermistor. In insulators, N is very low. Show that the equation I equals nAqv is homogeneous. What does that mean? We're asked to show that the equation works in terms of the units on each side. So the way to do this is to just note down the units that you've got for each term, and rather than writing A for amps for current, we'll write that as coulombs per second on the left hand side. That's equal to per meter cubed, which is N, times meter squared, which is A, times coulomb, which is the unit for charge, Q, times meters per second, which is velocity. And we see that on the right hand side, the m's cancel, and that leaves us with coulombs per second. So we've got the same units on each side, and that shows that the equation is homogeneous. Essentially, it shows the equation is valid in terms of the quantities and the units that we're using. So have a quick check now of your learning from this lesson. Do you know what is meant by drift velocity? Can you calculate the charge carrier density in a metal, given the size of one atom? Do you know and can you use the equation I equals nAqv? Could you define each term in that equation and apply it to answer questions? Can you apply I equals nAqv to explain the effect of temperature on the resistivity of metals and thermistors? So if you've got all of that, well done. If you need to go back and check anything, please do that, and you can rewind and watch sections of the video again if needed. Okay, thank you very much everyone. Bye for now.